Hi, and welcome to our lesson 3-4. Today we are going to be looking, as you can see from the title, for features that sometimes the summary numbers miss. And we're looking at a plot here of average longevity of mammals versus their maximum longevity. We've looked at these values before, but I've highlighted three of them. B for beaver, E for elephant, H for hippo. Really quickly, the beaver's average longevity is around 5 years, but one has been known to live to 50 years, which is pretty darn good for a beaver. The elephant has an average longevity of about 35 years, but one has been known to double that and live to 70. And the hippo had the longest of any of the average longevities, a little bit more than 40, but the maximum longevity was somewhere between 50 and 60 years, which is pretty good. Any one of those 3 points you could call influential, or to be considered influential, it must significantly change the slope, of the regression line, and the value of the correlation coefficient, or the value of R. And as you can see, any one of those 3 points may be able to do that. The hippo out here, if we were to remove this point, you can see that the slope of the line would be able to get a little bit higher because it won't be dragged down by the hippo point. Likewise, removing the hippo point would also change the correlation and make it a bit stronger. Removing the beaver point, I'm not sure that that would change the slope as significantly. As you can see, there are still 2 points here that are drawing it up and over, so I'm not so sure that I'd call him very influential. Removing the elephant point, even though it's the highest one on this plot, would probably not change the slope of the line very much at all, since you've got the beaver and the hippo drawing it out. So I'm thinking of the 3, the hippo is probably the one that is the most influential. However, to tell if you really have an influential point, you must really find the regression equation and the value of R with and without the point. Okay? Find the regression equation with and without that point. Again, looking to see significant change. Okay? Thank goodness our calculator does those calculations very quickly, so we don't have to worry about spending a lot of time doing it. It's just that something that we should look at. I'd like you to take a look at these 4 plots and pause the video and give a description. Remember, what you're talking about is shape, trend, and strength. Pause that video. Well, here are my descriptions. I said that the corner plot here is fairly linear. It does show an increasing trend, and it's moderate. It's not all close to tightly packed. This one is definitely curved, and it does increase to a given point, then it starts to come back down. As far as a line goes, you would not be able to say that this was a strong linear correlation. It certainly is not. Moderate at best. Okay? As you look at the lower left, this one also I say is fairly linear. It does have this point, which of course is going to change things, but there is an increasing slope to it, and any regression line would be heavily weighted by these points, but it would be dragged up by this one. I would call that a moderate correlation as well. This plot, I'm not quite sure what to say. Without this point, it's definitely linear, and it would be a vertical line. Although it does seem to show rise, but there is no run. As far as talking about a linear correlation, any line would have to come up to include that point, and that is just not a strong correlation at all. Oddly enough, folks, I want to show you my information here. Anscombe, who studied these things, said that the slope of each of the regression lines would be about 0.5 or 1/2. Y-intercept about 3 in all of them. So they'd all 4 have about the same regression equation, but only one of them is truly linear, according to Anscombe. He and I disagree. I think this one is somewhat linear as well. So if all you looked at was the regression equation, that can't tell you much. If all four of these have exactly the same regression equation, then that can't be the only thing that you depend on. So we want to talk about some other measures of strength in correlation. And a useful tool that we're going to talk about today to decide whether or not a line is a good model for a data set is called a residual plot. We've used the word residual before. A residual is the amount of prediction error for a given point. And you'll recall that we found that prediction error by doing actual y minus predicted y. Actual y minus predicted y. I'd like to have you take a look at the first Anscombe plot, and that's the data set that is showing here. I'm going to ask you to get your calculator. I'm going to get mine, and we're going to put these values in our list 1 and list 2. I have the scatter plot showing here. A residual plot plots each data value. So we're going to plot our x's versus the residual, that is the prediction error for each data point. In order for us to do that, we have to have a prediction line, and I'm going to go get that right now. Stat, over to Calc, option 4, and here's our regression data. As we said, a slope of about 0.5, a y-intercept of about 3. What I'm going to do with that now, I'm going to go into my lists and let my calculator lists help me out with this job. So I'm going to stat and enter. And in my list 3, folks, I'm going to ask it to give me those predicted y's. So in list 1 we have the data items, in list 2 we have the y values. List 3 we are going to make that predicted y's, and we're going to do that this way. On the title, we're going to ask it to paste the regression line in there. So we're going to paste the regression line into L3 using L1 for X, because that's where our data values are going to be stored in list 1. So here we go. It's going to be a vars, a 5, an over, an EQ, the same way that we pasted before. The only difference is we're going to arrow back until you find the X in the equation. And when your cursor is on the X, we want to replace that with list 1. That's where all of our X values are. So I've now made a prediction for each of my X values. To get the residual, you'll remember that that is actual y minus predicted y. Our actual y's are in list 2, so second 2. Our predicted y's are in list 3. So I want to just write out here, our list 4 is going to be the residual, and we're going to do that by doing list 2 minus list 3 on the title. Go ahead and hit enter, and here are all of our residuals. The residual plot is a scatter plot that for each X value shows its residual. So this is going to be a scatter plot, and I'm going to set that up here. Second and y equals. This time I don't want to be looking at lists 1 and 2. I want to be looking at lists 1 and 4, since list 4 is where I have my residual values. As far as a window, the X's will be the same. The Y's, of course, it's going to be the difference between what was actually here and what the line predicted. I'm not sure what those are, so I'm going to just zoom 9 to get a good fitting window. And I want to have you sketch that graph here. And then I want to talk about what it is showing. The heavy line through the middle, of course, is the x-axis, because some of our residuals are above, we predicted over, some are below, we predicted under. The line in the middle is the x-axis, and what you are looking for in a residual plot is no discernible pattern. Now I'm going to try and draw this. I'm not going to be perfect. Again, it's a sketch. And if the line is truly a good fit for the data, if the line is a good fit, you should see no discernible pattern in the residual plot. Now, I believe that this one isn't showing any discernible pattern. You don't see anything that looks curvy here. We've got dots above, we've got dots below. So this looks like a line is a decent fit based on this for that first Anscombe data plot. I would like you to practice making a residual plot now for the second Anscombe set. We'll want to follow the procedure that you just learned. Enter the X's in list 1 and the Y's in list 2. By the way, in the Anscombe plot data set 2, the X's are already the same, so all we have to change is our list 2. Once we have that in there, we want to call up the regression equation. We want to paste that in list 3, replacing X with L1. Once we have that in our list 3, we want to get in list 4 the actual residuals. So this would be actual Y in list 2 minus predicted Y in list 3. And then we want to see a scatter plot of list 1 versus list 4. All right, will you go do that, please? All right, I've come to the point where I have accomplished these things, all except I haven't looked at my scatter plot yet. In my list 2, I have this set of data values now. I've found the regression equation and pasted it into list 3, changing the X to L1 because that's where my X's are. In list 4, I have the difference, L2 actual Y minus L3 predicted Y. And now I'm ready to look at a residual plot. So I'm going to zoom 9, that's the stat fit window, and whoa boy, definitely seeing a pattern there. Here's the x-axis, and we've got a really nice parabola going here, which doesn't surprise us because of course when we looked at that Anscombe plot we could see the start of that. This has definitely got a pattern. That means a line is not a good model for this data. Definitely a pattern. The line's not a good fit. All right, and a good rule of thumb to think about is this. If the original scatter plot, if the cloud of points is elliptical, if you can draw an oval around the original plot, the residual plot should look random. Totally random. I'm going to back up one more time and demonstrate what we're saying. If you can draw an oval that fits around the cloud of points, that means that usually a line is a good model. That's it for us today. We'll talk about this a little bit more in school.